What's up everyone, welcome back to iCode Data. Today I'm going to show you a pattern that literally appears in over 100 LeetCode problems. And once you see it, you can't unsee it. We're solving the K-beauty problem, asked by Google, Meta and Amazon. But here's the thing, this isn't really about finding divisor in a number. It's about mastering the sliding window technique that will unlock an entire category of problems. In the next few minutes, you will learn why sliding windows are so powerful, when to recognize this pattern instantly, and a surprising truth about optimization that most people get wrong. Let's jump right in and build this intuition from the ground up. Alright, let's read through this problem together and really understand what they're asking. So the problem is called Find the K-beauty of a number. As written, the K-beauty of an integer num is defined as the number of substrings of num when it is read as a string that meet the following conditions. First, it has a length of k. So if k is 2, we are looking for 2-digit substring. If k is 3, then substring need to be of 3 digits. Second condition, it is a divisor of the given num. In short, each substring, when we convert it back to a number, should divide our original number evenly with no remainder. At last, we return the k-beauty of number. So we are counting how many substrings satisfy both conditions. Also given, leading zeros are allowed. That is, 0, 4 will become 4. And 0 is not a divisor of any value. If we get a substring like 0, 0, we can't attempt to divide by it. Division by 0 is undefined. And also, a substring is a contiguous sequence of characters in a string. This confirms we are looking at consecutive digits. Let's go through example 1. We have num equals 240 and k equals 2. So we need 2-digit substring. The first substring would be 24. 240 divided by 24 equals 10, which is a whole number. Also, second substring 40. 240 divided by 40 equals 6, also a whole number. So both substring works, therefore k-beauty in this scenario is 2. Also looking at the constraint, the number can be up to 10 raised to the power 9, which is a billion. That's at most 10 digits. So we are not dealing with massive numbers, and k is between 1 and number's length, which makes sense as we cannot have 5-digit substring in 3-digit number. This is a perfect sliding window problem because we are examining fixed size, consecutive, overlapping segment of our data. Each window shares k minus 1 digit with the next window, which is the hallmark of sliding window problem. Now let me show you visually how this sliding window moves across our number so we can build our intuition step by step. Let's start with our main example, where num equal to 430043 and k equal to 2. Here we can observe our first substring is 43 and 43 is a divisor. We can get a whole number 10001 as a remainder. So our k-beauty count will increment by 1. Our second substring is 30. That is not a divisor. Our third substring now is 0. We cannot divide by 0, so we will ignore this number. Our fourth substring is 04. That is 4. And 4 is not a divisor. And our last substring is 43. 43 is a divisor as we have seen before. So we will increment our k-beauty once more. So our k-beauty for this example is 2. Also we have seen 43 twice. That's perfectly valid. Different positions can yield the same substring, and if it's a divisor, we will count it every time. Now let's try one more example. Let's make our num bigger and also increase k to 3. So now we are looking for 3-digit divisor. Our first substring is 430 and 430 is a divisor. Our k digit will increase to 1. Second substring is 300, is not a divisor. Third one is 0, we cannot divide by 0, we will ignore this one. Fourth substring is 004 and that will become 4 and 4 is a divisor. Next is 043, we're going to ignore the prefix 0. 43 is a divisor. Our next substring is 430 and we have encountered it for the second time, but because it's a valid divisor, we will increment our k-beauty count again. Our last substring is 300 and that's not a divisor. So at the end, our K beauty for this example would be 4. Look at the sliding window technique box. See how systematic this is. First, we convert to string, make digit accessible. Position sliding window, we start with 0 and then we move. Third, extract substring, get K consecutive digits. Then we check divisibility if it's a valid divisor. And at the end, we update our K beauty count. This is the same process whether K equal to 2, 3 or 7. The window size changes but the algorithm remains identical. Now let's translate this understanding into code. So we are taking in our number and K and we will be returning an integer. That's our K beauty count. First thing, we will convert the number to string because we need to access individual digits. If I have 430043, I need to get 4, then 3 and so on. It's hard to do that with integer directly as they are stored as one big binary value, but a string, that's just array of characters that we can slice. Then we're gonna initialize our K beauty counter and we're gonna of course initialize with 0 to begin with. Now this is crucial. How many windows will we have? Think about it. If I have 6 digit and K is 2, I get windows starting at position 0, 1, 2, 3 and 4. That's 5 windows. This formula is always length minus K plus 1. And then we will iterate through each starting position. Here's where Python shines. The slice notation gives us exactly K characters starting at position I. Then we'll convert back our substring to an integer. So 43 will become numeric 43 and 0 for string will become numeric 4. Python handles the leading 0 automatically for us. Python uses short circuit evaluation. So first it will check if divisor is not equal to 0, and only when it is not equal to 0, it will divide the number by the divisor and check if the remainder is 0. If remainder is 0, we will increment our K beauty count here. And at the end, we will return the final count. And let's run through the logic one more time with our example. Say we have num 430043 and K is 2. The first iteration I equal to 0 will have substring 43. Divisor will be 43 numeric. And as we have seen, 43 completely divide 430043. So here the remainder will be 0 and our count will increment by 1. In second iteration, we will get divisor as 30. That is not a divisor. Our count will stay as 1. In our third iteration, we're gonna get substring as 0, 0. Divisor would be 0. We will fail the first check and we will skip and so on. The time complexity of our solution is O of n multiplied by k. And for the given constraint, this is actually optimal. As we can see in this heat map, each cell shows how many operations we are actually doing for different values of n and k. Remember our constraints. Number can be up to 10 raised to the power 9, which means at most 9 digits. So n is at most 9. See here, when n equal to 9 and k equal to 5, we do have 5 windows and 5 operations per window. That would be 25 total operations. That's our worst case, 25 operations. To put in perspective, your computer can do billions of operations per second. 25 operations will take about 25 nanoseconds. That's 0.000000025 seconds. Blink and you will miss it a million times over. Someone in the interview might ask, can we make the previous solution into ON? And our answer is yes, we can. But should we? We can share the pros and cons of both the approaches. So now let me quickly show you that ON approach. that would be rolling computation approach. So we will have that in our toolkit. Here is the code. We can see same initial setup. We convert to string, handle the edge case where k is larger than our number. Then we build our initial window. So for 430043 with k equal to 2, I will get 43. And we are using Python slicing to grab the first k characters. So we check if the first window divides our number. Now here where the optimization comes in. This power helps us remove the leftmost digit. If k is 2, power is 10. And if k is 3, then power is 100. So you will see why in the second. This line is doing 3 things in one go. Let me break it down with an example. Say our window is 43 and we are moving to position that adds 0. First, 43 modulus 10 will be 3. This removes the leftmost digit, that's 4. Then 3 multiplied by 10 will be equal to 30. This shifts everything left. Finally, 30 plus 0 equal to 30. Adds the new rightmost digit. So we went from window value 43 to 30 without rebuilding the entire number. Same divisibility check, increment count if it's valid. So what's the theoretical difference? The simple approach creates each substring and converts it. That's OK work per window, giving us O and K in total complexity. This rolling approach updates in constant time, just arithmetic operations, giving us ON. But here is the reality check, and this is important for interviews. After implementing both and testing them, there is not much performance difference for our given constraints. So why learn both? Because in interviews, you need to show you understand the theoretical optimization. That is, we can reduce from ONK to ON using rolling computation. You can implement if it asked, like I just did. You have a practical judgment. That is, given our constraints, the simple solution is cleaner and performs just as well or slightly better. My recommendation, start with the simple solution. Mention the optimization exists. Implement it only if this specifically asks. This will demonstrate both technical skills and engineering maturity. And that's what sets you apart. Now let's wrap up with some key takeaways. The key takeaway: great programmers don't just know patterns, they understand why those pattern works. When you understand why, you can adapt the pattern to new situations, optimize correctly, and explain your solution clearly. Please hit subscribe if this deep dive helped you understand this problem. Keep questioning why things work the way they do. That's how we grow as engineers. Until next time, keep coding.